think we're all familiar with uncertainty, so let's think of this as just revisiting some of the ideas and concepts that we're already familiar with. So it's a joint exploration. Right, so, would you agree? One thing is certain, that nothing is certain. Would you agree with that? I disagree.
Yeah? Okay.
Stop the originals.
I figured that.
Right. So we're going to look at uncertainty and climate change, how we deal with uncertainties, different types of uncertainties, and some of the things that we might do to adapt to coping with uncertainties. So it talks about prediction and resilience as different ways we can cope with it. If we think about how climate might affect us, might affect the weather, might affect water resources. There are a number of things that we're not quite sure about. If I'm thinking now in terms of the climate in a year's time, there are certainties about it, because we talk about there'll be a rainy season, but are we sure that we will get the average rainfall? We talked about that bell curve, and that, in a way, is a measure. It's giving us some measure of the uncertainty, because we're not sure. On average, we think it's going to do this. Let's leave out climate change for the moment. Leave that to one side. So we think we know, that it will rain next year. We think it'll rain in November more than in, let's say, August, but we're not quite sure by how much. So there are uncertainties in our perception of how much rain we might get. There's uncertainties in, as I say, will it rain more in October than November, or more in November than October? Does it make a difference? Now, let me go back to some experience, not maybe to illustrate the point, I hope a bit more forcefully. I used to work in Namibia. Now, for those of you who don't know, Namibia is a very dry country. It's got two deserts and a set of mountains in between. The rainfall, the climate and the weather for Namibia is actually, and it's on the west coast of Africa, southwest coast. Its rainfall comes from the Indian Ocean. So it comes across the continent. So by the time the moisture-laden clouds get there, they're quite tired. Dropped a lot of the rain. How much rain you get from year to year depends on what's happened in the other countries. And we would go for maybe 1 year, 2 years, 3 years without significant rainfall. And then all of a sudden, you get 5 years worth of rainfall in 1 year. So there's variability there, and the uncertainty, that talks to the magnitude and the timing in a certain way, because we weren't sure from year to year when that might happen. So we have those uncertainties. Then we have the other one, spatial uncertainty. We all know about spatial uncertainty, where it is. A couple of Saturdays ago, I was out with a running club that I'm with. We'd finished running, and it absolutely tipped it down where we were. So much so, I decided to get in the car, come home. I went 5 minutes down the road, and it was bone dry. And how often? We've all experienced that. So we have these uncertainties, and we can reproduce that on a bigger scale across both across the line. The problem we then have is that where we want water, where our towns and cities are not necessarily, I'm thinking more on sort of larger scales now, are not necessarily where our water resources are. We want water most of the time. For example, agriculture will want water. If you're growing crops, your crop demand for water is higher when it's hotter. But it so happens that it's probably the time of the year when you don't have rain. So we have this variability, we have this mismatch between what we need, we think we need, and what's available. There are also uncertainties. So changes, temperature, precipitation, characterized by this uncertainty. These things that we know about. I shouldn't really be spending as much time on it. But vulnerabilities as well, within society, within our infrastructure. It's probably not what they mean by this, but think of what. Who's from St. Lucia? You have a dam.
Yes.
You used to, sorry, I should say you used to have a dam.
We have one little bit.
Yeah. But the point I want to make, the John Compton Dam, Hurricane Thomas comes along. It's a properly engineered structure, designed by engineers, and you got a landslide.
Oh, landslide.
Yeah, into the basin. It is now, it's got more silt and sediment in it than it's got water in it. That's a piece of, you would have thought that an engineered structure like that with a nice pump station and pipeline going down would be robust. Vulnerability. To the extent now that they are trying to think of ways in which that dam can be desilted. Another vulnerability that arises from that is when you look at the intakes that there are on the intake structure. It is restricted, whereas before there were a number of intakes that you could take water from. There's only two now. Sorry, there were two, there's only one.
Water one is completely
stuck. So once the water drops below that intake, that top intake, even though there's water in the dam, you can't get it. Unless you float something on it. But what I'm just saying, there are sometimes vulnerabilities that we don't necessarily think about.
But to add to that, if we experience the drought that we had in 2002, we would have been in a serious jam.
Absolutely.
To get to the...
Yeah. What would have happened if Thomas had been followed by a period of prolonged low rainfall?
In the reverse.
Instead of the reverse.
In Thomas came before the drought of 2009.
Yeah. So vulnerabilities.
We have a dam for agricultural purpose dams and where it's located, even an excavator. Even an excavator has problems.
Yeah.
So sometimes the location is not selected.
So the point, there can be vulnerabilities in the infrastructure that we put in place. Even though that infrastructure was put there to address some variability and vulnerabilities that were there. And there could be other vulnerabilities that we've talked about, the social and environmental and economic vulnerabilities. Okay. Some of the, if we look at it in terms of what drives global climate, I'm not going to spend a lot of time on this, but some of the things that we've talked about already, and when we build these models that we've been referring to, these global climate models, We have to try and mimic natural processes. We know we can't do it. There are things that we realize affect climate or how climate functions, but we're not exactly sure. The melting of ice and snow. So how we know that white surfaces reflect sunlight. That has an effect on how much radiation is reflected back, affects global temperatures, the amount of energy, forget temperatures, affects the amount of energy coming into the Earth's system. If we have changes, but we're not quite sure how much those changes in that reflective capacity are, we don't know, for example, how much energy is reflected from different forest types. So trying to build some of those things into the model and take them into account can be difficult. When we're doing modelling, buildings model, we don't treat the atmosphere as one block. We divide it up into different layers. But each of those layers has different characteristics, as it has different types of clouds in them. They behave differently. Temperatures change as you go up the atmospheric column. So how do we take all that into consideration? So other ones that have come up recently, you may have heard, I put this last one in, you may have heard that the latest IPCC report has come out. And it has been noted, which we knew before, that temperatures over the last, 10 years or so have not been rising as fast as they were predicted to rise. So some groups of people have jumped on this and said, you know what that says? Climate change is driven by emissions. It's a myth. They may have a point, because one of the things that is difficult is to tease out the variability, because there are natural cycles in climate. There's, I'm going to get this wrong, Milankovitch cycles, which go over something like 12,000 years, that affect the Earth's orbit. Well, if your orbit is affected, it's affecting the amount of energy that's coming into the Earth's system, so that's going to affect climate. So we have variability, natural variability, but we also have imposed on that the impact of anthropogenic activities, and it can be difficult to tease out the relative contribution. So what has been suggested as one of the mechanisms is that, you remember maybe 20 years ago, CFCs from fridges as being responsible for the ozone layer in the Antarctic and the Arctic. And what happened? People got very concerned about it. They thought polar bears were going to develop skin cancer. But it was bad for the Earth's atmosphere. So they decided under, I think it was the Montreal Protocol, to ban the use of CFCs. CFCs are greenhouse gas, have had a huge warming effect, a bit like methane, as opposed to carbon dioxide. By phasing them out, that has had a positive impact on the warming process, slowing it down. So some have been suggesting that intervention is one of the reasons behind global temperatures not going up as much. So, but we're not sure. We haven't. It's one of these things that, by the way, that's a possible explanation, but we're not sure about it. So as we begin to understand how the Earth's energy system works, we're thinking of more of these processes. Ocean acidification. How much carbon is the ocean storing? And what effect is that having? How does that process of transfer between the atmosphere, the air, and the ocean, how does that work? How far down does it go? So there are uncertainties in our knowledge of how these processes work. In the projections themselves, there are uncertainties, and identified 3 sources of uncertainty there. Due to future emissions, due to internal climate variability, which is the green actually. Due to, sorry, I've got it the wrong way. Scenario uncertainty, internal climate variability, and intermodal difference. And as you can see, that when you put one on top of the other, as we go forward in time, our uncertainty increases as to where we might be going. Right. So where do we? This is sounding terrible, isn't it? Piling uncertainty on top of uncertainty. Where are we going to go with this? So, uncertainties in environment increasingly deal with situations where we are uncertain, values are disputed, the stakes are high, decisions are urgent. Right? And we have this idea where the stakes are high, the uncertainty increases. So where these are low, we have what we call applied sciences, which is where we'd like to be. Then we're getting into the other area of consultancy, and post-normal science is that science which is going beyond what we are able to conceptualize at the moment. This is the stuff that's really pushing the frontier history.
When you say weighing risk, weighing risk is a political task.
Sorry?
Weighing risk is a political task.
Weighing risk is a political task. That's what they're suggesting now. But that's what they're actually talking, that's what that says.
Yeah, but
they are weighing, a politician is weighing what you as a climate scientist are telling them might happen. They're looking at the implications for national development and economic growth, as well as whether or not they're going to benefit from this process. So the decisions that they are taking are probably more based on political considerations than just the science. And that's what that is saying.
and for our politicians, they're not so much exposed, I would say, to big business about
No, they're not.
as in the developed world. That is where I think the challenge is.
But it is, and I think we're not just talking of this as a political process within a Caribbean context. We're talking of this as a political task within a global context, because what's happening? Somewhere like China comes along, or a country that is very large and looks like China. Are they coming along and they're saying, you know what? I hear all these. I hear AOSIS. Sorry, not Oasis. That's a pop group, isn't it? I hear these people. They're coming along. Should I pay any attention to them? Because if I do, I'm going to rein back my economic development of my 1.3 billion people. Hang on a minute. Let me just check. How many people live on small island states? A couple of million. How much do I depend on them for my imports, exports, raw materials? Probably not very much. Can I therefore afford to ignore them rather than ignore my own constituency? Probably. So that's what I think is going on. It may not be it's a political process at the global level. But we're not always sure that, as we've seen recently, Chinese politicians have decided they need to rebalance their economy. Now, a year ago, we weren't aware of that. So there's a political uncertainty in this as well. Uncertainty, variability, risk and consequences. What does that mean? Let me try and give some substance to that. And I'm going to draw on the experience of Barbados, or my experience of Barbados, and maybe we'll broaden it to maybe some of the other situations. But uncertainty and consequences of climate change. Barbados, as you know, relies on groundwater. We're not sure under what conditions the groundwater aquifers receive their recharge. Now, when I say that might sound like a stupid statement, because you'll say to me, well, when it rains, it gets into the soil, it goes down into the aquifer. Well, not quite, because we have to take into account antecedent soil moisture conditions, the nature of the rainfall. If, for example, we get a month's rain in 2 days, most of that is going to run off from the surface because the soil and the underlying substrata cannot transmit that amount of water downwards in the time available. So we lose that amount of water, and the recharge, even though we've had a good bit of rain, the recharge doesn't take place. Or we might have long periods of time between rainfall events. And then we get rain that falls for 5, 10, 15 days continuously. But it does so at a rate that the ground can take it up. So I'm not sure, given all that variability, the effect of all this on my available resource. Also, I'm not, because I have a karstic aquifer with all the solution, I'm not sure what its storage capacity is. So there are unknowns in that. What we try and do is improve our predictions through modelling, things that Paulette was talking about earlier this morning. Trying to take into account temporal and spatial scales. Using new techniques. I mean, one of the things, for example, you mentioned was about downscaling. Real problem. I mean, talking to a water resource manager, a friend of mine, he said, you know, it's for me as a water manager, having a downscaled climate to at best we can do 25 by 25 kilometre grid. There's no good whatsoever. No point in that at all. It is unlikely that we will get the computing power to take it down further than to finer scales in the near future, I don't think. So what do we do? Throw our hands up? No, we look at others. So there's other techniques that we're using that will bring it down to catchment levels. But again, you have the question, how robust are these downscaling techniques? Adaptive management, look at different approaches. For example, we think of irrigation in agriculture. Would you recommend overhead irrigation, sir?
Depends on its crop.
Just in general. Work with me on it. No. Which is the answer that I was hoping for. Because various factors, it's not an efficient use of water. We could probably use drip irrigation or microspray or other forms of irrigation which would do the same job but with less water. We're working smarter. We're adapting the way in which we deliver the water to the the resource we have available and the climate we expect to see. So we could work a bit smarter, achieve the same goals with less input. So that's why the 2002 Johannesburg Summit was saying water use efficiency plans, that sort of thing. How can we think of that? An obvious, who mentioned leakage from systems this morning? I think somebody, but who's Paul? Right. So, for example, we have a new area we want to supply water to. We can't do it from the system at the moment. So what do? The engineer steps up and says, you know what, I've got a really good new resource. I'm going to build a big dam there. Because engineers love dams. Mr. Trevor there. He wants a dam named after him. They got the John Compton Dam in St. Lucia. They're going to have the Trevor Thompson Dam. You know what? A leakage reduction that will take it from 40 or 50 or 60% down to 20% would probably be a much better option. Adaptation. The only difference is we couldn't call it the Trevor Thompson leakage reduction.
Leave something behind, man.
So typology from knowing for the certain. I've got another slide a little bit later on that also deals with uncertainties. I'm not sure where it comes now. But we have other types of uncertainty. Statistical uncertainty. Are we sure that we are dealing with a normal distribution in our data, for example? Scenarios. How sure, how confident are we that our vision of the future is actually something that might happen? And scenarios are inherently things that won't happen in the way that we think that we project that they will, because of feedback mechanisms in there. We know there are some things, what was that? The known unknowns and the unknown unknowns. There are things that, for example, the aerosol that we talked about from the CFCs, before that we didn't know about it. We hadn't thought this was a thing, so there was some ignorance in there. What this is saying is that when our uncertainty is low, we can probably apply statistical techniques quite successfully. When our uncertainty becomes greater, as more things that we're not sure about, then we start thinking of scenarios. And you don't think, by the way, of just one scenario. When you're doing this sort of thing, you don't use just one scenario. You have to use a suite of scenarios with different assumptions made in them. Because what you're looking for are, under this spread of possible futures, are there common elements coming out? And those are the ones we would like to address. So if we find, I can't think of an example now, but if we look at scenarios for the future for improving water management, and we find that actually across the board, the use of economic instruments would reduce the amount of water that people use, then it starts to say to you, well, this probably is a very robust adaptation strategy, because under a number of circumstances it works in our models. Adaptation, well, following on from that table, we can see how we might deal with that uncertainty. We can either use predictions, and some of the techniques that we could use is there, but on the previous slide. So where we look at the likelihoods of the outcomes, we look at the likelihoods of their occurrence. Yeah. And that's where modelling helps us. isn't it? We can use models to help inform us. Resilience, where the uncertainties can't be removed, but we may be able to learn from the past. Could be things like what would be a more resilient strategy for Guyana might be to move all its agriculture away from the coastal zone, because there are certain uncertainties about flooding in the area. It could come from storm surges, it could come from floods, great floods from the hinterland. We're uncertain about that. We don't know if we can adapt to it. Therefore, a more resilient approach might be to relocate. The IPC approach is, you've heard these phrases, almost certain, likely, uncertain. They are actually attached probabilities to that. So whether they use scenarios to drive, and from the scenarios to look at the impacts, and then the other is the risk-based approach, where you look at the probability that something happens and the consequences. So risk equals probability times consequence. It sounds easy. A risk-based approach sounds easy. It's actually not easy at all. So how would we go about it? People have been thinking about identify the variables, create the scenarios, do the sensitivity analysis. See if you can identify thresholds. I think that's actually quite difficult. From the risk, say, well, if this happens, so what's the probability that this happens? What are the consequences? Usually consequences, we're talking about what? Money. It then says, at the last, consult with stakeholders. Joyce, would you leave it to the end there to consult with the stakeholders? No.
Deep trouble.
Deep trouble. Identify key climatic variables. Indigenous knowledge in some areas. So stakeholders can help with that. Creating of scenarios. Stakeholders help with that. Use some frameworks for risk approach. We look at the event itself. We learn from it, the extent of the damage. That obviously we reconstruct, but we try and learn some of the lessons. We look at prevention and preparation. So in reconstructing, we're applying some of these ideas of reducing the risk through risk and vulnerability of our infrastructure, of our populations. And then we know that extreme events will happen. Even without climate change, we know that will happen. So we have to plan for that. And so early warning systems, better collection of data, better models. One of the things that, for example, on the recent tornado in the Philippines, somebody remarked that 5 years ago they would only have been able to give a maximum of 1 day warning of where that typhoon would make landfall and the sorts of wind speeds to be expected. Today, they get 3 days. They said they were able to predict that 3 days because of advances in modelling and technology and data gathering. Where are we going to put our efforts? So one thing you do is you build up, you come up with index. Where is most vulnerable? So they've come up with this thing called Climate Vulnerability Index. It can be applied at different scales, but it takes into account resources, access, capacity, use, there is an example, I think, in the handbook of how it can be used. There's that nice diagram in there that shows that you know, how vulnerable different countries are, and capacity to manage and adapt. So that it relates to. And I think our friend who's left now talked about capitals. So social capital, individual capital, human capital, economic capital there. So if you like, some of that is reflected in there. What this one is trying to illustrate is that this sort of thing that is not a bad, it's a robust approach. It's robust up to a certain point. But once, if you get a storm surge that brings it, or a sea level rise that raises that level, and the freeboard no longer becomes sufficient for storm surges, that structure will fail. But what they're suggesting is that it could also be, if you design it in such a way, it could also be resilient, because you might design it in such a way that you could increase at a later stage the height of that structure. I would say that is one solution, but you should also be asking yourself the question, is actually having a structure like that the best solution? Should we perhaps not be having that protection there and allowing it to flood, allowing the protected area behind it to flood, and moving the people out of the area? Could that not be a more robust or more resilient solution in the longer term? Or there are other things you could say, are there things that I can do behind here, to the infrastructure behind here, like if they're buildings, or so we're talking maybe an urban environment, that would make those buildings more resilient and resistant to flooding. So for example, building everything on stilts, that could be a way, or raising critical infrastructure. And that's it.